Casimir force is actually an improvement of what we call van der Waals force. Okay, van der Waals force. I'm not sure if there is spelled with D-E-R or just D-E. Does anybody remember?
That's what you write is correct.
This is correct. Sometimes they use DE, sometimes they use DER. Okay. Because I'm not sure. Der means off. Okay, van of walls. That's what it means in European languages when you see der, it means off. Okay. I know of another Dutch person. His name is Peter Vandenberg. This is Van from Berg or something like that. Okay. There's another Dutch person I know is Adrian de Hoek. Okay, still means of hook. Okay. So what is this van der Waals force? It turns out that there's this other kinds of forces which is categorized under van der Waals force, is the London diffusion force. The London diffusion force. And what are these forces? It turns out that if you have a dipolar molecule, say a dipolar molecule will generate electric field such as this one. It looks like that. So if you put, say, another molecule next to it, the other molecule will get polarized. Polarized in this manner. Okay, the other molecule will get polarized. And then because of the charges being aligned in this manner, they tend to attract to each other. Okay, they tend to attract to each other. So the mere fact that you have another molecule next to one molecule, the other molecule will get polarized, and then these molecules get attracted to each other. And this is one source of the van der Waals force that explains why molecules stick to each other instead of falling apart. Usually, if you learn in your high school chemistry, they give you a rather naive picture of what a van der Waals force is. You have a nucleus, and then you have electron cloud, and another nucleus, and then you say, oh, maybe this electron cloud is here, and then this electron cloud is here, and then you have minus plus, and then this molecule tends to attack each other. But that is not a correct picture of what van der Waals force is. But you can take a quantum mechanical viewpoint of what this force is. You can think of these dipoles as simple harmonic oscillators. Okay, simple harmonic oscillators, and they oscillate in a simple harmonic fashion, each of them. And then the wonderful thing is that this force is there, even when the temperature is 0. When T is equal to 0, this force still exists. It will be bizarre, it will be very bizarre if this force disappears. And why this force exists is because if you have a simple harmonic oscillator, think of it as something that is bound together by a spring, and this thing would cease to oscillate when the temperature is 0. It would be in its ground state. The ground state is actually the 0-point energy state. And if this is a simple harmonic oscillator, we know that the energy is given by something like this. Okay? So even when n is equal to 0, there is an energy in this simple harmonic oscillator. And you learn from your quantum electromagnetics and quantum optics that the mean of the oscillation produced by the ground state is 0, okay, but the mean of the square is not 0. If you were to square the thing, you will find that it's not 0. What it means is that if this thing produces electric field, if this electric field is related to the ground state energy of this oscillator, then the mean of the field will be 0, but mean of the square is not 0. Okay, that's very important. So there's this n is equal to 0, which is known as quantum fluctuation of vacuum fluctuation. Vacuum fluctuation, it means that there is a field in vacuum even though when there's no electric field there. This field has zero mean, but the mean of a square is not zero. Okay? Because of the mean of a square is not zero, this fluctuating field can polarize the other molecule as well. And because this fluctuating field can polarize the other molecule, there remains an attractive force between molecules, even when you set T is equal to 0. When you set T is equal to 0, this oscillator will be in the ground state, but it still produces a fluctuating field. And it's actually wonderful to have this 0 point energy there, otherwise all these things will fall apart as we cool the temperature to 0. Okay, all the molecules will dissociate. That would be very bizarre in this board. Okay. So this van der Waals force has been known to exist, and usually when people calculate this force, they calculate using a very simple Green's function, assuming that the field, the potential, is proportional to 1 over r. Okay, and then 1 over r squared is a dipole, 1 over r is a monopole, 1 over r cubed is a multipoles, and so on. And this kind of potential is known as potential without retardation. Okay, no retardation. And many of the van der Waals forces were calculated that way, assuming that the dipole produces a very simple potential that has 1 over r. But then later on, when Casimir came about, and then he introduces the fact that that's not correct. Velocity of light has a finite velocity, and that the potential should behave something like that, and this is with retardation. And then it's often said that the Casimir force is actually van der Waals force computed by including the retardation effect, by assuming that the velocity of light is finite. If you assume that the velocity of light is infinite, if c goes to infinity, you get back this kind of potential again. Okay? So we can do some simple Casimir force calculation. And there are actually two or three methods of calculating Casimir force. One is actually the stress tensor approach. Sometimes it's called a Maxwell stress tensor. It turns out that if you have an electromagnetic field, E and H, somewhere in vacuum or space, okay, if you put an object in the vicinity of this E and H, this object will feel a force. Okay, it feels a force because there might be V cross E forces acting on this object, and there might be Q times E kind of force acting on this object. And this thing will feel a force. And you can actually derive this force using Lorentz force law. Okay. But there's a better way of doing this, which I wouldn't derive, but I just put the result. Okay, let me see if you can find the result. Okay, I can just put the result of what is usually stated in the textbook, like I took this out of Kong, okay, that if you have a Maxwell stress tensor, which I denote by a double bar, then you can show that divergence of this stress tensor plus partial G, partial T, this is a vector, okay, is equal to the minus the force applied. What is G and T? G and T G is considered the momentum, the electromagnetic momentum is given by D cross B. Okay. G is given by D cross B, and T is the Maxwell stress tensor, is given by D dot E plus D dot H times the identity tensor minus two outer product BE and BH. Okay. I will derive this. You can derive this starting with Lorentz force law and then going through Maxwell's equation and show that this identity is true. So, in order to understand this identity vector, you might want to express this in the integral form. So if you take the volume integration of this, you will have this. ds. First of all, you would take the dv, okay, you take the dv of this over b, then by invoking Gauss law, you get this, and then you have partial t g dv, okay, over the volume is equal to minus f dv, okay. So you can see that this is a vector, this is a vector, this is n dot t. T is a tensor, so n dot t is a vector. So this says that if you have a stress tensor which is given by the presence of electromagnetic field, the presence of electromagnetic field can create a stress tensor, and we take this quantity and integrate over the surface of the object, and then you calculate the tau, I mean the t at that point, okay? And then that thing dotted with n will give you the force actually acting on this surface, okay, in that particular direction. And that particular direction is n dot t, okay? N dot t need not necessarily be pointing in the same direction as n, and then the S is just a small area, and this thing exerts a force in that small area, and we sum over all these forces on this small area. Each of them will have a torque, kind of a force acting on them if you do this integration, and then this gives you the total force on this object, okay? With this object is sitting in the presence of some D, E, B, and H, okay? But you can look at console. You can look at console that is derived in it, okay? But I wouldn't derive it. So the thing about this is that if you have a vacuum field, sitting out here, vacuum field is supposed to be no field. The mean of D is equal to 0, the mean of E is equal to 0, and the mean of all these are 0. But the mean of the product would not be 0, okay, because this is quadratic. This is not linear. So if you have a vacuum field, if you're in the ground state, if your n is equal to 0 ground state, the 0 point energy will contribute to a non-zero stress tensor. Okay, will contribute to non-zero stress tensor, and you can actually integrate all those forces over the surface of this object and find that force. And I had a paper with one of my former PhD students, Xiong Jie, and she did some calculations for me. Essentially, if you know how to find a vacuum field, then you can find a force on this object as being the expectation value of the stress tensor over the surface of the object. Okay, this would be the force acting on the surface of the object, and if you apply that to two objects, for instance, you find that these two objects actually been pulled to each other. So one way to look at the existence of Casimir force, say if you have two metallic objects, okay, if there's a vacuum field present in these two PEC objects, for instance, perfect electric conducting objects, then the vacuum field will polarize the charges on these two objects. Okay, they will polarize the charges. There's supposed to be no field there, but the fluctuating field will polarize these two objects and then try to pull these two objects together. And that is one way to regard as to how Casimir force comes about. You can think of it as very similar in spirit to this picture as well. Okay, the electric field polarize the object get charged, oppositely charged, and then they get pulled to each other. And then in the paper that we wrote, the ij component of this stress tensor, if you work those things out, is given by EI Ej plus 1 over mu naught EI Ej. Okay, this is an outer product. It comes from things like that. Okay. Do you know how to read indicial notation? Does everybody know how to read indicial notation? These are called index notation. This is a index notation for a tensor. Second rank tensor, this is index notation for a vector. When you write two vectors like this, it means it produces a tensor because this is an outer product. So if you write something like this is called an outer product because there's no dot in between. And in indicial notation, this translates to EI Ej. This means that this is equal to some kind of a tensor, a second rank tensor. Okay? And it has two indices. And then this is the outer product again. Okay, I think we use that kind of thing in a course sometime, right? This is the outer product. And then there are other terms that result from the inner products. Okay. So you have k equal to 1 to 3, then ek to the power of 2. This is the inner product. And then you have another term that comes from another inner product. K equals to 1 to 3 delta ij. Okay, delta ij is this other tensor that you have over there. Okay, so those are the stress tensors that I did not derive, but you can look up any classical electromagnetic textbooks. You'll find this stress tensor been derived. Okay? But the wonderful thing is that if you have a ground state, which is the n is to the 0 state, this expectation value of this stress tensor is not equal to 0. Okay, we know how to write this in a course in terms of operators. The field can be written in terms of operators. And assuming that all the electromagnetic fields are in the ground state, if you were to take this expectation value as we have learned in our course, this is always equal to 0 if you're in the ground state. But if you take the product of two fields is quadratic, you'll find that it gives you a non-zero term. And this is due to the fluctuation of the field, and it can be related to actually the direct Green's function of the medium. This is a diode, okay? I wouldn't derive it again. This actually follows from the fluctuation dissipation theorem. Okay? What does the fluctuation dissipation theorem say? It's something that is quite commonly used in electrical engineering, especially when we want to calculate noise in circuits. Okay, we like to calculate noise in circuits. That is that if you have a resistor, okay, and say if it's connected to a maybe to another load, okay. This is R. If this resistor is in a thermal bath, if this resistor is in a thermal bath, then there will be fluctuating electromagnetic energy in the environment of this resistor. And if it's in thermal bath and in thermal equilibrium, what happens is that this resistor has to give up energy to the environment as much as it is absorbing energy from the environment. Okay, so it's very much like the black body radiation thing that we studied. Okay, when this thing is in thermal equilibrium, and then you can show that the energy, the voltage square induced by this fluctuating field in the environment of this resistor is proportional to kBT. Okay, this is like the kinetic energy of the environment. You can learn about this law from the equal partition energy theorem, and that this resistor will acquire that kind of energy, and then actually the energy is proportional to the bandwidth times the frequency, something. So the thermal energy that this resistor has acquired is proportional to the temperature, the Boltzmann constant times the bandwidth of the signal. This is the bandwidth in which you measure this energy over. Okay? So this thing will be in terms of watts because you multiply by this frequency. So this is like V squared over R kind of thing. Will be proportional to that quantity. And hence the thermal noise that you acquire from the environment is always proportional to temperature. It's always proportional to the bandwidth of the signal. And this law is actually a special case of Planck's law. Planck's law says that the distribution of the energy is proportional to something else, and I don't correctly remember the formula now. Maybe H omega over 1 minus e to the minus H omega over kBT. This is Planck's law, right? So if I plus. So if I make h bar omega very small, Planck's law becomes this is 1 minus h bar omega over kBT. Okay, we learned about Planck's distribution. So if you take h bar omega very small, then it is proportional to kBT. Okay, so Planck distribution law becomes a classical distribution law in the limit when h bar goes to 0. When h bar goes to 0, you get this. So this is like the classical limit of Planck's law. It's been used by electrical engineering a lot. If you calculate thermal noise in your circuit, you invoke this law, which is actually a subset of Planck's law. And the fluctuation dissipation theorem says that the kind of energy that you can acquire from the environment is proportional to this thing, because you're in thermal equilibrium. And similarly, the fluctuation dissipation theorem says that if you have a very complicated object, okay, this object is going to be in thermal equilibrium, the environment is going to be in thermal equilibrium with the rest of the world, and you're going to acquire some energy around, or some E field around this thing, and that E field is proportional to this thing, which I will not derive, but this thing is essentially a relationship between G, E, is the Green functions times J. Okay, so G acts like we know that J is equal to sigma E, E is equal to maybe rho times J. Okay, so in the resistor, rho plays the role of the resistor in this kind of thing, but in the greater, more complicated generalized sense, the Green function plays the role of the resistor. The Green function plays the role of the resistor, especially the imaginary part of the Green's function. So if you take the imaginary part of the Green's function, it plays the role of the resistor. So it has a kind of a thermal equilibrium law like that. which roughly speaking is that B squared is proportional to K dt FB times R. Okay, times R. So you can think of this as R, and then when you integrate over this is the bandwidth, and then there is something missing here that is not in Planck's radiation law. Planck's radiation law, or Planck's distribution, should actually be rightfully augmented with an additional term. That this E, this energy that we often use in Planck's radiation law, is usually written like this. But Planck never included this term, which is a 0-point energy term. Okay? The 0-point energy term. So if you let T go to 0, it actually says that the E should become just that. Okay? And if you allow for that fact, then the T actually disappears from this formula. This is for T is equal to 0 formula. Then only the ground state. The ground state is contributing to this force. Okay, only the ground state is contributing to this force. And then you have this 0-point energy that produces a force. Where the Maxwell stress tensor, you can actually calculate the forces between two objects using this kind of approach. And then we have other expressions too, which I wouldn't write down, but we have similar expressions for the expectation value of the magnetic field. Okay, equal to something like this on the right hand side, a lot more complicated. And using this kind of thing, then you can calculate the Casimir force for very complicated objects. And in that case, she did calculations for some complex object that is shown in this paper over here. So that's a Maxwell stress tensor approach, which can be used to calculate the force between very complicated objects. But the key is actually in finding this Green's function. Finding this Green's function, one resource to classical electromagnetics. That is actually the dielectric Green's function. You naturally have to solve Maxwell's equation. The dielectric Green's function satisfies this kind of equation. Okay, I won't bother to derive this, but I'll just give you a rough idea. Rough idea as to what this dielectric Green's function is. You probably have seen something like this, scalar Green's function. Okay, you probably have learned this in your ECE487, right? And this is an exploded version of this for electromagnetic field. And you have the dielectric Green's function, then you can do calculations like this. This is the elevated form of the scalar Green's function. Okay? So let's see. The other approach of calculating the Casimir force is actually through the energy approach. What you do here is that you say that you have two complicated structures. And say if it's enclosed in the cavity. Okay? And then there will be resonance modes that this cavity has. Of course, for some simple shapes, we know how to find those modes. Like if you have two parallel plates in an infinite vacuum, you know how to find the resonance modes of these two parallel plates. If the cavity is just a small box like this, then you know how to find the resonant frequencies. And this one you also know how to find the resonant frequency. But for a general structure like this, we do not know how to find the resonant frequency unless we resort to some numerical methods. Okay? Say if you have the resonant modes, then all those modes can become simple harmonic oscillators. And each of those modes will have a ground state, a 0-point energy. And then we can actually calculate the total energy of this thing, and then it will be sum over half h bar omega j. Sum over all j. This is the total energy, the 0-point energy of the system. Okay? So you can actually calculate this. You can resort to analytic methods when you have a parallel plate, and when you have something like this, you can actually find those modes in closed form. You resort to numerical methods when you don't have a closed form solution. And then the 0-point energy of each of those modes will be something like this. And then you ask yourself that, say if I have a simple structure like this, then this 0-point energy is proportional to B. B being the separation of the plate. Okay? So in order to calculate the force that has been exerted on these two parallel plates due to the presence of vacuum field, vacuum fluctuating field, then I actually can change the separation a little bit and then calculate the new resonant frequency that I will find. I just moved the two objects a little bit apart, calculate the new resonant frequency, calculate the sum of the 0-point energy, and then the force will be proportional to, the rate of change of this energy, the 0-point energy with respect to the separation. And that is another way to calculate Casimir force. Okay. And why is Casimir force interesting? Well, it is interesting because it has been thought to exist way before. I think is it Van Coder? Maybe the other guy's name is Van Coder. Van Coder and Casimir calculated this force many years ago, and it's calculated based on the fact that a quantum mechanical system has a 0-point energy, and many people don't believe in 0-point energy, but that maybe they shouldn't exist. But it wasn't until 1997. 1997, Lamoureux, okay, it's a French name. But he's American actually, he works at Yale now. Before that, I think he was at Los Alamos. Okay, he did an experiment to establish the existence of this force. And by 1997, our knowledge has greatly improved. And this is the age of nanotechnology. You probably recall that before 1997, there was no nanotechnology, very little nanotechnology. After 1997, whole slew of experiments comes about because of the advent of nanotechnology. And Lamoureux was able to do some experiments to establish the existence of this force. So people became very interested. And why is this force important? Because when you do NEMS and MEMS, nano electromechanical system, micro electromechanical system, you have small moving parts. You have small moving parts, and those parts will tend to stick to each other, giving rise to a phenomenon called stiction. Okay, stiction. And we would like to know how to avoid this stiction force in NEMS and MEMS, because suddenly they snap together because of this kind of forces. Another thing that has been established is that if you coat this material with an appropriate kind of material, you can actually get this force to be repulsive. Okay, and this has been shown by Carpasso. I don't know whether it's 2P or 2S of Carpasso. Probably no. He's a very famous guy. He also did things like quantum cascade laser, and recently he does work on metal surfaces. Okay, and then he also did experiments on Casimir force. He showed that by taking the combination of materials properly, you can engineer forces and causes them to be attractive in the state of repulsive, or repulsive instead of attractive. Okay, so he showed that repulsive force possible, and this is good knowledge because this field is a very young field with very little knowledge. So if you know how to engineer things, where things are repulsive, then perhaps there are other applications for this kind of forces. Okay. So let's go through a very simple calculation of the energy-based method using this approach. Are there any questions so far? Okay, let's assume that we have two parallel plates, and then and this is a nice textbook problem because it can be solved in closed form. You know how to solve this problem using your ECE487 kind of knowledge. Okay, you have two plates and then they're separated by D. And then you have L in one dimension and L in other dimension.